Hello, I'm back with the last proof. Um, proof 12, which is of the exterior derivative. Um, okay, so we're going to start up with a differential form on R square, which looks kind of like phi is equal to f of xy dx plus g xy. It's a smooth differential form on R and you're gonna state the definition of d phi dx e2 and then try and show that this thing is equal to or rather not that thing but rather d phi is equal to um, dx g minus dy f dx dy. All right. Um, cool. Since okay, so I'm gonna start off with the thing that we know about this um, function. All right. So we do know that phi is a one form, and that would mean that d phi will have a two form. And we need to figure out what that really does of the basis vectors e1 and e2. So we can write down d of p as a1 2 dx dy. And to find a1 and a2, we're going to calculate the derivative of this on some parallelogram which is anchored at some point. And to do that, so let's go about doing that, which looks kind of like so d phi dx e1 into the limit of h tends to 0 1 by 8 square integrating from px h1 h2 phi. All right. Now that's what we're trying to do. So to integrate over this boundary, and this thing that we call a parallelogram, um, we kind of have to do all the little segments of the parallelogram and then figure out how much those segments are changing by, and then integrate along those segments. Uh, I'm gonna draw down a handy dandy diagram of said parallelogram, um, and then show you what exactly I mean by that. So this is x, y. This is the point that we are anchored at. And then along the first segment, it's only the x values which are changing by some h, where we're going to later sort of use limits to show that the h tends to 0. And yeah, and the same thing the other direction along 2, which is going to be um, x plus h, y plus h. Um, along, I don't want to do that. Um, along 3, which is going to be x, y plus h. All right, this is the segment, the fourth segment. All right, so we have all the numbers, and now we got to calculate what the what the values are when we integrate along them. So for the first segment, we can parametrize this 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 segment as something like gamma of t, which is equal to x plus ht y, because it's only the x component that's changing, and this t ranges from 0 to 1. Uh, then the Jacobian for this thing is going to look like, and when we differentiate the d gamma of t, is going to look something, we can skip the t. D gamma is going to look like h0. Alright, um, and then we sort of let the differential form that we had act on this Jacobian that we just got. So d of x is acting on d gamma to give us h, and in this case dy d gamma is going to be 0, because that's the only thing that's changing. Um, so in this case, the original phi, or the differential form that we had, looks something like fxy dx plus gxy dy, and the contributing exterior derivative in this case, by plugging this back into this thing that we had, is going to look something like 1 by 8 square, which we what we got from before, 0 to 1, it's actually t equals 0, um, f of x plus ht, which is the parametricized form that we have, h dt. Alright, so this is along segment 1. Then we're going to do the next one, which is on side 3, also because it's going the other way and it's going to be easier to do this. So in case of side 3, it goes from uh, x plus h and y plus h to x and y plus h. So in this case, we already know that it's only the x plus h term that's changing. So when we parametrize, oh my god, parametrize this, it's going to be something like uh, gamma t is equal to x plus ht y plus h, and then t goes from 1 to 0. Uh, and the Jacobian for this thing, again, because we're differentiating with respect to t, is going to be d gamma is equal to h0. Again, we sort of figure out what the contribution of this is going to be using this form, and that looks like 1 by 8 square equals 0, 1 f of x plus ht y plus h dt, and we can now combine this factor that we got for the first side. This is what we got for side 3. We combine them together to get, I'm actually going to copy all of this stuff down because it's less work. Have them together. I think did I mess up the sides? Yeah, should be a 1, this should be a 0 because we're integrating from 1 to 0. So in this case, and then we can factor out the h's um, to get 0 to 1 minus 1 by h f of x plus ht y plus h minus f of x plus ht y dt. Alright, now we know that, now from mean value theorem we know that the above thing can sort of be written as 1 by h 0 to 1 h d y f of x plus ht y plus hs dt is equal to some value which is like 0 to 1 dy of f x plus ht y plus hs dt. Alright, now once we do take the limit of h tends to 0, we get something like, in this case, we get something like minus of dy of f x y. And this is a contribution from sides 1 and 3. Now for side 2, we're going to do this kind of the same thing. It's laborious. D is equal to, in case of side 2, where is the handy dandy? In case of side, I'm going to sort of cover what I'm going to change. So in case of side 2, we're going to only change the h value here. That's what we're that's what we're trying to put into the parametric form. So this is the only t value that's going to change from 0 to 1. The same thing in this case, but this is going to go from 1 to 0. Alright, so this is going to look something like x, y plus ht, and t ranges from 0 to 1. And then the Jacobian and the corresponding contribution for this, the Jacobian for this is going to be 0h, and the contribution for this side is going to be 1 by h squared, 0 to 1, that's what we are integrating against, g of x plus h, y plus ht, h dt. Similarly, in the other case, we're going to have gamma t is going to be equal to x, y plus ht going from 1 to 0, and the Jacobian for this thing is going to be 0h, and the contribution is going to be 1 by h squared, 1 to 0 g x y plus ht h dt. And again, we're going to combine this similarly as we did before to get 1 by h, integrating from 0 to 1, g x plus h y plus ht minus g x y plus ht dt, and this thing is going to be 0 to 1 d x g g of x plus hs y plus ht dt. Alright, again we're going to take limits as h tends to 0. We're going to be left with the same thing, which is d of x, g, x, y. So now we can combine all of these things that we kind of did, which is, I don't know why I just wrote a del instead of d. D of phi, calculating the exterior derivative, so e1, e2 is equal to dx g xy minus dyf xy. So we got d phi is equal to dx g minus dyf. This is just in differential forms, dx dy, which is kind of what we wanted to show. Thank you for staying for my proof.